All right, hello everyone. Today we're going to talk about the open circuit test and short circuit test. The open circuit test, the report for it will do next week. I mean this week. For the short circuit test, we'll do next week in 2 weeks. Please follow in campus. I'm going to post. You can see the report or lab 4. Uh, is it lab 4? Yeah, lab 4 and 5. So yeah. So what kind of losses in the transformer? There is copper losses. The copper losses is basically the winding is created by using a long wire and wrapped it around the core. And because it's so long, we have to account for the losses in the wire. If it's a small wire, it's neglectable, but in the transformer case, it's not neglectable. So we have to encounter for that. And the winding is used in the primary and the secondary, both of them. The other losses is the leakage losses. Basically, the magnetization created uh, by the wire is not captured, or the force created by the wire. Once there is a current flowing in the wire, it's not all of them captured by the core. So some of them is leaked out. And the other two losses, which is the core losses, or another name for it is iron losses, is the hysteresis losses and eddy current losses. I'm going to talk about this in the coming slide. The most common mistake, I'm going to talk about it in this case. So the equivalent circuit is basically R1 and X1, and those representing the primary. One is the primary, and R2 and X2. I know this is not X, it's L, but that's X mean the ohm in this case, but this is Henry. Now, now you can refer to the primary side or the secondary side. Now this is referring to the high side, which is the primary side. If you want to refer all the parameter to the primary side, what you're going to do is you can basically multiply by A square. A is basically the turns ratio. We found out how to get the turns ratio from the previous lab. Now pay attention to this in his case. R1, we're not touching R1. We're not touching X1 because it's already in the primary side. We're not touching that. We're only doing the R2 and X2. This is if we were to refer the equivalent circuit to the primary side. If we refer the equivalent circuit to the high side, now we're not touching our X2 and R2 because it's already in the high side. Well, this is depends on the experiment and where you place, but for our experiment, we're not touching that. We're only gonna take R2, R1, excuse me, R1 and X1, and divide it by A square. A square is basically the turns ratio. Yeah, this is basically it for that. Now for the hysteresis losses, if I have two coordinates, the y coordinate representing the flux, which is the inside the nail. I have a wire wrapped it around the nail, and I have a battery. Now, battery is a DC. We usually talk about AC when we talk about power system, but I'm gonna use DC to illustrate the concept of hysteresis losses in this case. Now, the x-axis is the magnetization force created by the wire. Sometimes some of the hysteresis losses, they represent the x-axis by the current going through the wire, which is the same thing almost. Now, at the beginning, the nail has no magnetization in it, so it's not magnet. But if I connect the battery, the current will flow in the wire, and it's gonna build the magnet. Now the current will build, and the magnetization, the nail will be magnetized. It's basically it's gonna be a magnet. If I take off the wire, the magnet will reduce, but it's gonna remain the same as it's gonna remain. It's gonna save some energy on it. Now if I flip the polarity of the battery and connect it, the magnetization, the force will be reversed, everything will be reversed, and it's going to build, as you can see in the graph, like this. Now, if I disconnect it again, it's going to go back. Now, there is no current at this point. There is no current, but there is magnetization. Basically, we reverse the north and south of the nail, and so on and so forth. And this is what is called the hysteresis losses, if we talk about AC current. Now, for the ED current, if you were to look into the nail, it's a solid metal. And if it's a solid metal, that means the ED current is basically circulating inside the metal. So in order to minimize the ED current as much as we can, we slide the metal and isolate them electrically. There is insulation between each piece. It's basically sandwich, but they're not touching each other. The current will not flow, but the flux will. Yeah, so this is the primary, and the primary is from the other side, and this is the secondary. Now, the concept for this does not apply only for the transformer, but anything that require magnetic force. An example of that, if you have this kind of motor, like you can find it in any toy kits, just open it and see. You're gonna find out something like this. Open it. This is a summary of it. So we're basically gonna implement two experiments. The first one, open circuit test, due this week, and short circuit test, due next week. The open circuit test is to get the magnetization losses, and the short circuit test will get the other losses, which is the copper losses and the winding. Now, if you're concerned about like in the test bed, this is how we implement it. We connect the AC side to the input here and neutral to the input, and the output. This is for the power analyzer, and the output will go to the transformer, and the other side will go to the other transformer. This is the primary, and this is the secondary. Now notice we did not connect the second winding. Open circuit test. We want to see how much power the transformer is getting in this case. Now for the short circuit test, this is the short circuit test. Now it's the same connection. The A is going to the input, neutral is going to the input, and the output is connected to the primary, secondary, and this is a short circuit test. This is one of them. Now this is the measurement for it. This is the current, the voltage, the power angle, power factor, and this is the power, which is watt. This is amp, sorry, this is amp, voltage, the unit amp, voltage, and watt. Now this is not correct due to the power analyzer accuracy. It's supposed to give 0 point something. This is what it did with the open circuit test, 0.8. This is correct, but this is not correct. Not correct because if we make this as 1, that mean if we make for the short circuit test, that mean we don't have the imaginary number. It's only R in this case, which is not correct. Now let me talk about the Simulink model. Now for the Simulink model, display. Now this is a Simulink model for open circuit test. I'm going to provide the short circuit test soon. Notice this, the source is connected to the transformer, reading the current going from the source to the transformer and measuring the voltage going to it. I mean the current across the two terminal. Now the other side, which is the secondary side, it's remained open, no load connected to it. I'm going to take the current, voltage measurement. I'm going to say power, electrical specialized power sensor and sensor measurement system and this. And run it. You should get something. Now, what are you gonna do? This is requiring the peak value, but 140 is the RMS value. If you multiply by square root of 2, you're gonna get the peak value. Now, for your experiment, you're gonna change this to 2 and run the experiment. For now, I'm gonna leave it at 1. And you're gonna get this value. This is the power, as you can see here. This is the RMS value for the current, and you're gonna do the calculation as it's provided in the report. If you have any question, please reach out to me. Thank you.